Is the audio bouncing now? Is it bouncing? Do you see the little bar there? Okay, cool. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. I thank you for your many, many blessings to us each and every day, Lord. I just pray that you just work in people's hearts to elect the right people today, Lord. In your name I pray. Amen. Well, I guess it's not the election yet, but it does seem like today matters. Let's see here. All right, so I'm going to prove for you guys, to start with, I'll give you a proof of L'Hopital's rule. And before I do that, of course, I have to prove Cochise's mean value theorem. Oh, come on. This is a new marker. What? This is like psych. Let's see how this new marker works. Okay, well, whatever. 50-50. Cochise's mean value theorem. All right, so you suppose f and g are differentiable on the open closed interval a to b, and we also suppose that g prime of x is not equal to 0 for all x in ab. Then there exists a r in a to b. All right, there exists some number in the open interval a to b for which f prime of r over g prime of r is equal to f of b minus f of a over g of b minus g of a. This is not, this is kind of like the mean value theorem, but it's certainly not the mean value theorem. What's the mean value theorem say? In words, it says the average rate of change over some interval, over some duration of time, let's say, is equal to the instantaneous rate of change during some instant of time during that duration, at least one time. Now this, we're going to be able to prove by something called, basically by Rolle's theorem. Do you guys remember what Rolle's theorem says? You forgot it. Well, I'll remind you when we get there. All right, so we're going to let the change in f be f of b minus f of a, and I'll let the change in g be g of b minus g of a. I would point out to you that these are just numbers. A and b are fixed, and by the way, we're also going to assume that f and g are as stated in the theorem. Okay. All right. Let h of x equal to, and here's the sneaky trick. What you do is you let h of x be f of x minus f of a, all right, times the change in g plus the change in f times g of x minus g of a. Observe, h is both continuous and differentiable on the closed interval from a to b. Why is that true? How did we construct it? H is what? It's formed from adding functions together, from multiplying functions by given numbers, right? These are all things which don't change the fact that the result is continuous or differentiable, right? It's clear that h is the sum of continuous functions multiplied by numbers. And likewise, differentiability also follows through from basically from rules of differentiation and rules of limits. It's clear that h is both continuous and differentiable, okay? More than that, though, we can calculate h of a. What's h of a equal to? H of a is what? F of a minus f of a delta g plus delta f times what? so you said it's 0 because this, right, it's 0. This is 0. That's 0. So 0 plus 0, still 0. Now, on the other hand, h of b is what? There we got f of b minus f of a, delta g, right, plus delta f. Not, oh man, I did the same thing I did earlier. Yeah, that would be 2 delta g delta f, except I made a mistake. Apparently this mistake is canonical in my proving. I made the same mistake earlier. However, as per the custom of the usual earlier class, it took us about 5 minutes to find it. We found it this morning, though. We did find it. This is supposed to be a minus. All right, which makes this a minus. Which makes this a minus. So in other words, what we have is we've got delta f delta g, yeah, minus delta f delta g, otherwise known as 0. So you guys forgot Rolle's theorem. It's unfortunate. Look at this marker, all right? You guys, you watching? It's very complicated. So study just the y element of the motion, right? The initial height and the final height was the same. Rolle's theorem says somewhere in the motion there's a y velocity of 0. It says, Rolle's theorem says this: if you have a function such that the value of the function is equal at a and b, right? If that function is continuous and differentiable between a and b, there must be some point such that the derivative of the function is 0 between a and b. You could say it's a special case of the mean value theorem where the average rate of change is 0. So by Rolle's theorem, which applies to h, there exists an r in a to b such that what? H prime of r is equal to 0. But what is h prime of x? Well, let me write down h prime of, what's h prime of r equal to? Differentiate, right? H prime of r is f prime of r, right? Times delta g, which is just a number, minus delta f times g prime of r. Now, what happened to the g of a and what happened to the f of a when I differentiated? They're just numbers. They differentiate to 0, right? Then all we got to do is solve this thing, right? We solve this for f prime of r over g prime of r, and we get what? Delta f over delta g, which, by the way, is f of b minus f of a over g of b minus g of a. And that, folks, is Cauchy's mean value theorem. Now, if you're thinking, right, you should say, wait a second, not so fast, mister. How did you make that last step, right? Well, the answer to that question is algebra, but that algebra requires some commentary, right? So I'm going to save this for later because I need it. Otherwise, I'll forget to do it, and I don't want to do that. So ignore this for now, if you don't mind. So let me discuss star for just a second here. How do I know that I've divided by g prime of r? Well, g prime of r is not equal to 0 by assumption of the theorem, right? Right, because r is a particular thing. It's a particular thing in the interval where we're assuming that g prime of x is not equal to 0. What else do I need in order to do that algebra? I need g prime of r is not 0. What else do I need? I divided by the change in g, right? Why is the change in g also not 0? It's just a number. If g of b was equal to g of a, what would that say? Right, that's the trouble. If that were the case, I couldn't divide by delta G, right? That would mean delta G. This is equivalent to saying delta G is 0. What's the problem with saying that G of B is equal to G of A? Well, apply rule. No, I mean, I'm not saying A and B are equal. No, what?
It didn't state that A equals B.
I'm sorry?
So, like, I think Rolle's value theorem works if, G of B equals G of A.
Right. So is Rolle's theorem true? Yes.
Right.
We apply Rolle's theorem to G. What does it tell you? Given that G of B is equal to G of A, what happens? Rolle's theorem tells you that there exists some other number C between A and B such that what? G prime of C is equal to 0. But that is impossible because we're given that G prime is never 0 in this interval, right? Therefore, by contradiction, hence G of B is not equal to G of A, as G prime of X is not equal to 0 for all X in AB. So it's impossible for that to happen given the preconditions of the theorem. It's just not a possibility that G of B is equal to G of A. Because if it were, Rolle's theorem would say that G prime was 0 somewhere. But it's not. That was given to us. So my algebra is right. And we're done. Yep.
So how did you take the subtraction of those two terms and turn it into a division?
Algebra. So I add 1 to the other side, and I divide by G prime of R and divide by delta G. And it gives me that ratio, the equality of those ratios.
Okay, 0.
I mean, some of you probably should be like, well, this is great and all, but what does this have to do with L'Hopital's rule? I mean, fair enough. So how's this L'Hopital's? Oh man, I hate to erase this stuff. Fine. So if, oh, come on. Stop that. If, no, it's dead. It's just dead. Off the wall. It's here. If, let's say f of x and g of x both go to 0, as x goes to 0, a c from the right, and f and g are differentiable to the right of x equals to c. I mean, differentiable, let's see, to the right, let me be more precise. They're differentiable on, let's say, c to, say, c plus epsilon for some epsilon greater than 0. And if you have g of x and g prime of x not equal to 0 on this interval, all right, and I know it keeps going, and you also have that f prime of x over g prime of x tends to gamma. Let me use the limit notation, sorry. X goes to c from the right of f prime of x over g prime of x. If this is equal to gamma, then, punchline, limit as x goes to c from the right of f of x over g of x is also equal to gamma. This is a special case of L'Hopital's rule. So theorem. I mean, this is L'Hopital's rule, basically. Here's the proof. Try to be brief here. Assume f and g are as above. Now what I want to do, by the way, this is in section 5.4, I believe. Or maybe, wait a minute, no. 5, listen to me. 11.5, that's what I meant. Page 555. Nope, still wrong. 557. I'm basically at the bottom of the page at the moment. All right, so first of all, an observation. If f and g are differentiable, right, that implies that f and g are continuous, right? And here I mean at x equals to c, okay? So what does that mean? The limit as x goes to c from the right of f of x, and the limit as x goes to c from the right of g of x is equal to what? Continuity says it's equal to g of c. Oh, good grief. F of c. Why would I put g there? That's just nuts. Okay, so this is g of c, but what are those? It was given to us in the theorem. We're assuming that those limits are 0. All right, so consider then, by Cochise mean value theorem, we can do the following. We can, well, this isn't Cochise mean value theorem just yet. So this is this. See, I can take the quotient of f of x by g of x and trade it for basically the change in f over the change in g from c to x, right? Yes, sir?
Is it g of x not 0?
Yeah. So I haven't stated that right. There we go. A very, very good question. I wonder if I did that wrong in the earlier class. Odds are probably yes. Now, it is, however, the case that if you think about it, right, if g has a non-zero derivative, think about this. If g has a non-zero derivative to the right of the limit point and g of c is equal to 0, what does it mean if the derivative is non-zero? Can there be any other values for g which are 0 nearby? No, there can't, because the function's strictly increasing or strictly decreasing to the right of c, given that the non-zero-ness of the derivative. It can't have a turning point close to the limit point. Just saying. I digress. All right, so back here, f of x minus f of c, g of x, right? I just subtracted 0. Then what? Now we apply the Cauchy's mean value theorem, right? To what? To the closed interval, what, x to c, right? Oh, sorry, other way around. C to x. Here x is I should say x is an element of what? X is somewhere in c to c plus epsilon, okay? I'm picking some point where I have that the derivative is non-zero, all right? Some point in this c to c plus epsilon, close to c but to the right of it, all right? That's where x is. We draw a picture. Here's c. Over here is c plus epsilon. X is like here. I'm applying Cauchy's mean value theorem to an arbitrary x in here on this closed interval like this, all right? This is the closed interval that I'm applying the Cauchy's mean value theorem to, okay? So Cauchy's mean value theorem says that there exists an R, right? There exists an R in that little green strip somewhere in there, say here, right? Such that what? This is equal to f prime of r over g prime of r, right? You can see it from this, right? You can see clearly that what? If you take the limit as x goes to c from the right of f of x over g of x, right? That's equal to the limit as x goes to c from the right, right? Of f prime of r over g prime of r, just using what's above. What happens as x goes to c from the right? What happens to the r? What does it do? It pushes r to where? See what happens to r? Pushes it to c, right? This has to be equal to, the limit as x approaches c from the right of f prime of x over g prime of x. Agree? That's just a substitution. And we're done. See, because if the right limit is equal to gamma, the left limit is also equal to gamma. And that's L'Hopital's rule. Are you guys troubled by this? Yes?
If it was like C from the left, would you just do C minus?
Right, c from the left, then I'd have to study like c minus epsilon, and I'd apply Cochise mean value theorem to like an interval where c was on the right, and then the x would get pushed towards c from the other side, but basically the same argument goes. I showed the earlier section. I'm going to show you guys too. This is not a bad argument. It's pretty careful. It's a nice argument, but there's another way you can look at this. If we're a little bit greedier, and this will give us a little bit more intuition about where L'Hopital's rule is coming from. So here's a greedy argument. So assume that f of a is equal to g of a is equal to 0, and f and g are continuously differentiable at x equals to a, with g prime of a not equal to 0. Continuously differentiable, what this means, all right, guys, is subtle. It means that the function is differentiable and its derivative is itself continuous as a function. All right, so here's the trick. You look at the limit as x goes to a of f of x over g of x. All right. And what you do is you say, okay, well, that's equal to the limit as x goes to a of f of x minus f of a over x minus a over g of x minus g of a over x minus a. See what I did there? Kind of sneaky business, but I subtracted 0 and I divided the top and the bottom by x minus a. I'm free to do this in the limit of x approaching a because, of course, the whole point of the limiting process is that we approach a, but we don't actually get there, right? That's the cool thing about a limit, is I can divide by x minus a in the limit, whereas if x is equal to a outside the limit, I can't do it. It's just a fine line that the limit walks. Anyway, so you can break this up into a quotient of limits. I don't think this is in your book, but it's in a lot of books. Anyway, everybody should see this, so that's why I'm showing you. Now that step is only valid in as much as the limits which result exist, right? And the one downstairs has to be non-zero, otherwise this limit law just isn't the case. What's the top, though? Definition of the derivative, remember that? Or not? I don't know. F prime of A. Downstairs you got yourself a G prime of A. Now, if the derivative is continuous, this is the same, of course, as the limit as x approaches A of F prime of x over G prime of x using the continuity of F and G, both respectively. And there you go, L'Hopital's rule. You notice that Cauchy's mean value theorem, I did not assume continuous differentiability. Not assuming continuous differentiability exacts a high price from us. Devin? No, you're Isaac, right? I've got Devin's notebook. Although I think I have your test. Yeah. And in here. Or maybe not. Maybe not in here. Oh, man. Any questions while I'm doing this very fascinating activity? All right. Can you, that's actually kind of a funny question. History is probably the case that L'Hopital was not the discoverer of this rule. I think it was, I forget who it was. It was maybe the Bernoullis or I don't know, one of these characters back in the day. L'Hopital was the first to write a very popular and widely used, let's say, I think it was widely used. I'm not sure. You can still read it. It's open source if you can do the French. It's, about from 1801, something like that. Lagrange had a big calculus book from like 1780, something like that. But this kind of a follow-up to that. And L'Hopital had this rule in that calculus book, and I think it's part of the reason it's called L'Hopital's rule, although technically he's probably not the originator of the rule. Anyway. Continuous differentiability makes proofs easier. That's just something generically you'll see as you go on in analysis. The other thing is, of course, we can also derive a rule as x goes to infinity. It's at the end of the section. I'll let you look at it there. Basically, it says that you can, we have this identity, the limit as t approaches as x approaches infinity of f of x is equal to the limit as t approaches 0 from the right of f with 1 over t in the place of x, right? So this interchange between limits at infinity and limits at 0, this duality, allows you to basically steal L'Hopital's rule at 0 and move it to infinity through just like a little chain rule argument, basically. It's at the end of the section. I'll let you look at it. So this proof that we've done then extends to infinity at least. Now we've proved about 30% of the L'Hopital's rules we actually use. See, because now you guys think about this. I'm going to erase that since we don't need more. How do we actually use L'Hopital's rule? This is like the statement of the theorem versus how do we use it. Do you see the difference? What does the theorem say? It says if what? If the derivative, the limit of the quotient of the derivatives is given, then the limit of the quotient of the functions is the same, right? How do we use L'Hopital's rule? We do what? We start with this, right? Then we write like L'Hopital's rule 0 over 0, infinity over infinity, whichever the case may be. And what happens? So it's like the thing that the theorem, so the theorem says this needs to be given, right? In order to conclude the thing over here is valid. So why is that the theorem we need to prove? Here's another example of this kind of logic. How about this? If you have the limit of f minus g, right? It's what? Limit of f minus the limit of g. when you use that rule, how are you using it? When I talk to Calculus 1, I tell them that whenever we do something like this, right, more often than not, we're doing what I would say is I would call it taking out a logical loan. The only way that this is valid, right, is if these things actually separately exist. In the same sense up here, this is only valid if that actually exists, right? So this step in the end is justified after you do a few steps, and then you find that you work your way from something that's indeterminate, 0 over 0 or infinity, to something that's determinate. And then in retrospect, that series of steps you made was logically valid and justified by limit laws. But in the interim, you're just going off a hunch, right? I say that, but that's actually not the case. Like L'Hopital's rule is more generally true than this. Like this fails. In the case that these don't exist, for example, here's a simple example. X goes to infinity of x minus x. Well, that's 0, because that's the limit of 0 as x goes to infinity. It is certainly not the case that that's the limit as x goes to infinity of x minus the limit as x goes to infinity of x. This is infinity minus infinity, and they're not the same infinity, although they look like the same infinity to you. Those are separate infinities. We cannot cancel them. In other words, this limit law is not valid because the resulting this and that don't exist. L'Hopital's rule is kinder, though. L'Hopital's rule actually still makes sense in the case that the quotient blows up to infinity, or a few other divergent things. So like L'Hopital's rule is a little bit, like I said, it's a beast, and it's a little bit more forgiving than this in that sense. Anyway, I'm going to shut up about that. So that's one last thing. What's the intuition for L'Hopital's rule? You can kind of see it right here, right? It says that if you have something where f of x and g of x are both going to 0, right? Or both going to infinity. We haven't proved that case. Apparently, if the rates are so comparable, like they're both going to 0, like their values are close to 0 in the same way, well then instead of looking at their values, you can look at their derivatives and compare which one of them is going faster, right? You can compare how fast they're going to 0. If their speeds are still nearly identical close to the limit, you could apply L'Hopital's rule again, and then you can compare accelerations and see who wins, right? If that doesn't work, if the accelerations are also comparable, the problem, like I told you earlier section, the problem's a jerk. You have to compare the derivatives of the accelerations, the jerks, you know, and look at the quotient of that, and you can just keep going and looking at higher and higher and higher order data. When two functions are so similar to each other, it's hard to see which one wins as you study a quotient going to the limit point. And I mean, that's what this proof essentially shows, is that intuition is valid. But anyway, whether or not you understand the intuition of L'Hopital's rule, you can still use it, right? Successfully. I'm not sure that this intuitive comment I added really adds much to L'Hopital's rule. Can I erase? Oh, I'm going to. All right, guys. So do you guys have any questions about I have a few minutes for homework. Do you have any questions about homework?
Number 60.
Uh-oh. Oh, man, is that right? We end at 10:30, don't we?
No.
Oh, okay. I feel better. Man. What about it?
What does it mean to fix t?
Fix t? It means t is a constant, and take the limit as k goes to 0 from the right. So it means you can treat t as if it's equal to 2 or something. So for example, fixed t, the limit as k goes to 0 from the right of e to the minus kt would equal to, well, I don't know. See, it depends in this case. Fixed t greater than 0, how about that? Then this is kt, well, that's a small negative quantity, right? So this is just, I mean, exponential is continuous there, so I mean, it's just e to the 0, this is just 1, that's stupid. Sorry. Limit as k goes to infinity may be more fun, I don't know. 0, I mean, t is fixed. Yeah. Other questions about that one? Number 25 and 11.6. Ah! Yeah. Yeah, that one's a lot like the one I sadly erased right here. So let me show you the one I erased for a second. Did anybody have questions about the hyperbola asymptotic one? It's related. I'll get to your question in just a second, Steve. So the other question that's kind of like this one is this: if you look at x squared over a squared minus y squared over b squared equals to 1, this is a hyperbola, right? If you solve this thing for, well, if you multiply by a squared, you get x squared minus a squared over b squared, y squared equals to a squared, which gives me x squared minus a squared equals a over b quantity squared times y squared. If I solve for y, I get b over a square root of x squared minus a squared, at least in a certain place. And so you can look at this, the hyperbola has asymptotes, right? And so, believe it or not, I will eventually get to your question. So this is really just the solution in the positive y. Now, what does this look like? Hyperbolas either open up, or they either open up like this or like this, right? So you can tell which one it is by just putting x equal to 0. Put x equal to 0, I get minus y squared equals to b squared, a very hard equation to solve with real y. In other words, this equation, the graph of this equation, does not contain any points on the y-axis. So this thing, this hyperbola, opens up sideways, like so. All right? So the notion of a function being asymptotic is, well, think about this right here. If x is much, much greater than 0, then what? Then y is approximately b over a times x. Right? Because, I mean, essentially the square root of x squared minus a squared is just the square root of x squared. X being positive, that's just x again. So my point is, asymptotically, if you get really, really far out there, all right, like that, then these two things get really, really close. And he gives a definition in one of your homework problems about two functions being asymptotic. We say that f and g are asymptotic as x approaches infinity if the limit as x goes to infinity of f of x minus g of x is equal to 0. So, to show that this hyperbola is actually asymptotic to its asymptote, which I would hope is true, right? We need to check what? You need to study the limit as x goes to infinity of what? Of b over a times x minus b over a times the square root of x squared minus a squared. That's one of your homework problems. All right, that's kind of related to this one. Let me work the same one I worked for the other section because it's nice and easy, and then I'll work something like the one you asked me about. because it's the same song and dance to solve these. So a very related problem. So I'm trying to show you why this kind of limit is interesting. It's interesting because it answers the question of whether the function x and the function x squared minus 1 or plus 1. What do you guys want? Plus 1, minus 1? Plus 1? Fine. Okay. I want minus 1. Sorry. I don't mean to do that to you guys. It annoys me greatly. My wife's like, what do you want to eat? What do you want to eat? What do you want to eat? I'm like, pizza. She's like, okay, we'll have rice noodles. Like, I would have been fine with the rice noodles before I said the other thing. Just whatever. Pick your favorite thing. Whatever. I mean, anything but pizza. Okay, so this is type infinity minus infinity. Now, before, if you think back to algebra, we gave you stuff like 1 over x plus a root or something like that. And then you had to get the radical out of the denominator and into the numerator. Well, now the tables have turned. In order to use L'Hopital's rule, we need to make a mess of this thing so that it becomes a fraction. So what you do is just kind of undo the trick. Or do the trick, depending on how you want to look at it. But actually, the way I'm solving this problem is the same as the way we're going to solve the one you asked me about, Steve. So this is, so I get myself an x squared minus the square root of x squared minus 1 squared. Notice that the plus x times the root and the minus x times the root cancel. That's the whole point of doing that. And now the x squareds cancel. And you get minus 1, which gives you, just 1. Yeah, which is 0. So in fact, yes, y equals x and y equals the square root of x squared minus 1 are in fact asymptotic. That's good, because y equals x is the one of the asymptotes of the hyperbola. X squared minus y squared equals to 1. Now, you asked me about a different problem. You asked me about what's the limit as x goes to infinity of, what was it, x minus, something like this, right? Oh, the other way around? It was number 16, was it? 25. Oh, okay, sure. I'll change that 2 to a 3. I'll leave you something to do. Sound like a plan? It was 3 or 2 in the problem. What was it, a 3 or 2 in the problem? I forgot. 2. I'll make it a 3. There. Now it's a different problem, so I'm not doing your homework. Haha. Oh. Now you know what to do that I showed you the thing above, right? What do you do? I think we can just do root x squared plus 3x plus x. So I get myself x squared plus 3x minus x squared, right? I like this example because I want to take it and make it worse. So this, x squareds cancel. What do you got? Now, you might be tempted to do L'Hopital's rule here, and of course you could, but it's wiser to just use algebra, right? So divide the top and the bottom by x. How does that go? So what I just did is I was like 1 over x times the square root of x squared plus 3x, right, is what? That's really like 1 over the square root of x squared, yeah, right? So there's the details there to go into, let me call it star, in particular this. So what's the answer? 3, right? So here's a fun.
3 over 2, right?
Oh, 3/2. Okay, fine. Thank you. Yeah, kind of shame to. If you like, by limit laws, this is 3 over 1 plus the square root of 1 plus 0, also known as 3 over 1 plus 1, also known as 3/2. There you go. If you think more writing is good, there's more writing. All right. So here's a fun question. If you work this out, what's asymptotic to this? Here's a way to make this problem more interesting. We can answer a corresponding asymptotic question. So like y equals the square root of x squared plus 3x, right, is asymptotic to what? Which is really totally unsurprising if you complete the square on this, right? Of course, as x goes to infinity, that just becomes like x plus 3/2. So this is totally unsurprising. Oh, they say minus 3/2. Oh, I'm uno momento, plus 3/2, right? Sorry. Plus 3/2. Yeah, plus 3/2. Sorry. I'm visualizing the trouble. See, because if I subtract 3/2 to the other side and then rewrite this as like x plus 3/2 subtracted from this, then the limit as x goes to infinity of the square root of x squared plus 3x minus parentheses x plus 3/2 by our calculation above is 0. Because I know that the difference exists in 3/2, it follows that these must, this converging also gives me that converges to 0 is my point. Which tells me, in fact, that the square root of x squared plus 3x is asymptotic to x plus 3/2. I don't know. I think it's interesting. You can disagree. If you want. So anyway, another thing that would be interesting to think about here is, how does this problem change, right? What if I was to take this problem and instead of, any questions about this? Everybody caught up with me? Yeah? Go ahead. So I want to modify this problem just a little bit and talk about the subtleties which are involved. What if instead of going to infinity, I go to minus infinity? All right, and to make it interesting, I put a plus here. How does that change the game? It's still infinity minus infinity. It's indeterminate, right? That puts a plus here, right? So you wouldn't multiply by plus x over plus x, you do what?
Multiply
minus x over minus x. That much is obvious, all right. Then what? This step is pretty much the same, right? It still comes out to x squared plus 3x minus x squared. So you still get down to this. Almost the same problem, right? There's a minus down here. Oh, yes, thank you. That's important.
Shouldn't it be minus x plus that unless we multiply it by.
Minus x, not minus the
Oh, yeah. Sorry. I'll tell you, I'll put a minus up here to make up for that, if that's okay. Yeah. Tell you what, I'll take my medicine. There you go. You guys happy? All right. Now then what? Now, at this point, star is no longer valid. See, because if I have a minus, all right, so what I have to have is, if this is a minus x, right? See, minus x is equal to the absolute value of x is equal to the square root of x squared if x is less than 0. So I don't bring x's inside square roots, I bring minus x's inside square roots. Right? So this is valid.
Just divided by x once again.
I can't do it. I can't bring x into the root. Can't do it. So like this, I have to divide by, let's say I divide by minus x. I get minus 3. I get 1. And this, I in fact get, let me do it one more step here. Minus 1 over x squared plus 3x. You guys with me so far? I'm just dividing the top and the bottom by minus x. Just a second. I'm dividing the top and the bottom by minus x. Now your question. Yeah.
Why can't you just write it as negative square root of x squared?
You can't write what as negative square root of?
Over here on the right, the star.
I don't understand. I'm sorry.
Like, you say x is less than 0.
Yeah.
So why can't you just write it as negative square root of x squared?
That is minus the absolute value of x.
And you wouldn't have to write x less than 0.
X is less than 0, though, here. I'm considering the limit as x goes to minus infinity, right?
Yeah.
I mean,
Yeah.
the point is in order to simplify this algebraically, I can't bring x inside the square root. I have to bring minus x inside the square root. That's an important thing to understand because that means that this minus doesn't get left outside. In fact, it gets drawn inside because there's another minus which is hidden implicitly within the x. So this is the limit as x goes to minus infinity of minus 3 over 1 plus the square root of 1 plus 3 over x, which, by the way, is minus 3 over 2. If you don't pay attention to this subtlety, you will convince yourself that the limit diverges when it actually doesn't. Because if you don't, then you'll get 1 minus 1 downstairs, which will make you think that you're dividing by 0 into a finite quantity upstairs, and you justifiably say it blows up. But it doesn't blow up if you do the algebra correctly. So I'm just telling you, you got to be wary of this issue. When you're dealing with negative x, be careful with roots. Okay, you've been warned. That may or may not be an issue in any of your homework problems, but it is nevertheless an issue in math. Your homework is just a subset, right? The homework is the minimal amount you should do. You probably need to do more to really understand. Thankfully, I have not assigned all the problems in the book, right? You can do more if you want. the grader has finite time, so we have to deal with it. Okay, with that, I move on to the next section, which is, so there'll be more time for your homework questions tomorrow, and then we'll have a quiz tomorrow on the L'Hopital's and the sequences again. So basically everything in chapter 11, except for, I'm not a monster, I won't test you on improper integration just yet. I mean, there's no point in it tomorrow. Well, there's really no point in testing you on L'Hopital's rule either if you haven't done your homework yet. And if you haven't done your homework yet on L'Hopital's rule, if you haven't started your homework in a significant way, you're being very foolish, I'll just say that. Okay, so improper integration. There are two kinds of improper integration. All right? There are the ones that are just manifestly improper, something like integral from 0 to infinity of e to the minus x dx. All right? So here you have infinite bounds, something like this. All right? Well, I guess I would say this more to the point. We have improper bounds. The other thing that could happen, though, would be something like this. You could have something like dx over the square root of x from 0 to 1. So here you have an improper integrand, right? And then you can also even have things that have both, like, for example, integral from minus infinity to infinity of, I don't know, dx over x, for example. Now, I could give you the different definitions in the different cases and state them formally and abstractly. I don't think it would accomplish much. What I want to do today is just communicate to you how we make these definitions. And the answer to that question, I mean, that is really just, we define it in the most natural way possible. Wherever there's something which is not defined, we approach that, whatever that is, in a limit. So, for example, the first thing, what do we mean by the integral from 0 to infinity of e to the minus x dx? What does that mean? Well, what you do is you simply take the limit as b goes to infinity of the integral from 0 to b of e to the minus x dx. That's all that means. What else could what else could you possibly mean by that? Well, let's not think about all possible definitions. That seems like a hopeless task. All right, so limit as b goes to infinity of, and you can do this integral, right? That's e to the minus, minus e to the minus b plus e to the 0. Because minus e to the minus x is an antiderivative, and I can do the fundamental theorem of calculus, part 2. Right? You guys with me? This integral we can do. These limits we can take. What's the limit as b goes to infinity of e to the minus b? 0. So this is 1. Geometrically, what's going on here is we've just shown that the area under this curve from 0 to infinity, this guy I'm shading, that is area 1. It's an infinitely long shape, but it gets to be, the height goes to 0 in such a way that the area bounded is finite. In fact, it's 1. Kind of neat, right? The second example, what do we mean? What's the trouble with the second example? I mean, in some sense, the second example is not a very good example because you could get this right without doing it right. So